In 1924, geologist Noel Odell climbed up the side of Mount Everest and found something unexpected had beaten him there. Odell and the rest of his team were some of the first people on Earth to climb 7,700 meters up the mountain. But when he dug up fossils like these out of the mountainside, he realized that somehow a bunch of ancient ocean-dwelling invertebrates had already made the journey. You heard that right, ocean-dwelling, near the top of the tallest mountain in the world. How is that even possible? Hi, I'm Sage, and this is Crash Course Geology. Last episode, we talked about plate tectonics, the idea that Earth's outer layer, the lithosphere, is broken up into plates that are moved around by heat from Earth's mantle and gravity. And today, we're looking more closely at how plate tectonics has created the landscape around us. Like, have you ever looked at a beautiful mountain view and just been speechless? Or maybe wondered, how'd all that happen? Well, we're about to find out. Tectonic forces, along with other things like water flow, volcanic and glacial activity, and even humans, push and pull on rocks in the lithosphere. That's called stress, or the force that's placed on a particular area of rock. Aw, are you a little stressed, Wayne? Could we get him some chamomile, please? To picture what geologic stress looks like, imagine if this candy bar is a piece of land. If I press on it, stretch it, or torque it to the side, I'm applying stress, just like those forces do to the lithosphere. Stress comes in different types. Compression, which squeezes rocks together, tension, which pulls them apart, and a sideways force called shear that moves them in parallel but opposite directions. Under enough stress, the candy bar will deform. It can smush, stretch, or tear right in half. Those are examples of strain, the physical changes that result from stress. No, don't worry, Dwayne, you're an indoor rock. No one's gonna smush you. For rocks, and candy bars, that deformation can happen in a few main ways. Got one for you too, bud. One way is through plastic deformation. If you push or pull on the candy bar, it'll bend. In the same way, when certain types of rock experience high heat and a slow rate of strain deep under the surface, they can permanently bend their shape too. Now imagine the candy bar went back to its original shape after bending. In geology speak, we'd call that elastic deformation, where the rock returns to what it looked like before it deformed. But if the candy bar's been in the freezer, it won't bend, it'll snap. Thank you so much. This is like brittle deformation. When forces act on rocks closer to the surface, they can break. Brittle deformation creates a fault, a deep fracture or zone of cracks in the ground caused by surface movement. And that's where lots of geologic activity happens. Like when the ground pulls apart through tension, the result is often normal faults. This happens when the rock above the fault moves down relative to the rock below. You'll typically find these at divergent plate boundaries, like the one that forms the underwater mid-Atlantic ridge. On the other hand, compression can create reverse faults, where the block on top moves up and over the one below. We call it a thrust fault if the angle is shallow. You'll often find reverse faults at convergent plate boundaries, like the one at the heart of the Himalayas. Geologists call it a megathrust fault because it's really big and shallow. Shear stress can create strike-slip faults, where two blocks grind past each other and cause all kinds of geological chaos. Strike-slip faults can form long valleys and sharp cliffs, and even change the flow of rivers. When they sit along plate boundaries, we call them transform faults, like the San Andreas Fault in California, where a lot of earthquakes happen. I've experienced half a dozen earthquakes on this fault, including one where my granny and I were upstairs and my grandpa was downstairs watching TV. I noticed it first and I called out earthquake, but my grandpa couldn't hear over the TV, so when he did get what I was saying, he yelled, "What? I can't tell," and then the old man jogged upstairs during an earthquake out of pure FOMO. Love you, Papa. Earthquakes don't happen only at transform faults, though. All kinds of faults can cause them. In fact, the largest earthquake ever recorded happened at thrust faults, like the one that devastated Chile in 1960. We'll get more into earthquakes in a later episode. Whew, that was a lot of geolingo. How you doing, Dwayne? Yeah, I feel you, bud. Let's head back to Mount Everest to talk about how this bad boy was made. It's located in the Himalayan mountain range, where two plates collide at a convergent boundary. Compression, the type of stress that squeezes rock together, is the main force behind orogeny, or mountain building. Compression causes uplift, or the raising of Earth's surface. When that happens at the boundary between continental plates, like it did with the one between India and Eurasia millions of years ago, there can be massive results, namely the highest mountain peak on Earth. As for where those marine critters came from, well, at the same time as the Indian continent plate was moving toward the Eurasian plate, an oceanic plate at the bottom of the prehistoric Tethys Ocean was subducting. Essentially, it was sliding beneath the Eurasian continent, pulling India along with it. When the two continents hit, the huge force of compression caused the land to crumple and buckle together, shoving rock upward. As the Tethys ocean floor subducted, some of it got scraped up by the moving continents and left behind. All that sediment from the ocean floor built up between the continents and formed an accretionary wedge, full of rocks and, fossils from deep down under the sea. India kept on moving, and that accretionary wedge got shoved further and further up toward the sky, forming the Himalayas. And that motion hasn't stopped. Today, India is still pressing toward the rest of Asia, building those mountains up higher and higher, as much as a centimeter a year in some parts of the range. Yeah, you thought sea life on the top of a mountain was going to be the mic drop moment. Nah, Everest is getting taller. But not all super tall mountains stay super tall. Like, once upon a time, the Appalachian Mountains of the US might have been as tall as the Andes. But tectonic shifts aren't squishing the eastern edge of North America anymore, so they're no longer growing. In fact, they're shrinking. Over the years, weathering and erosion from wind and water and ice have worn them down and will continue to do so long into the future. When it comes to compression, it's not all about mountains. It does other cool stuff too, like it warps rocks into curves or sharp points called folds. They take the shapes of arches, troughs, or step-like bends. And while folds change the shape of rocks, compression can also change the rocks themselves. As mountains form, some of the rock is not only squashed, but also buried deep underground. As their minerals transform under high heat and pressure, the rocks become metamorphic. This transformation can cause layering, called foliation, which can look like this. Like this. So when you're driving through the mountains or reaching the peak of a hike, you're taking in thousands of years of movement on Earth's surface. Put that in your Insta caption. But as we know, plate tectonics doesn't just push the land together, it also pulls it apart through tension. Instead of thickening, the crust thins out, deforming the land in different ways. Like when the surface is stretched at divergent boundaries, the rock can break into a group of normal faults, forming landscapes like this. The series of raised blocks are called horsts, and the sunken ones are called grabens. Horsts and grabens? Who named these? Lewis Carroll? If the tension is high enough, those valleys in between can get really big, like this. Rift valleys are whole regions where two tectonic plates pull apart and cause the land in between to sink way down. One of the biggest is the East African Rift Valley, which runs all the way through East Africa, from Jordan down to Mozambique, where two plates are slowly sneaking apart. In some places, the valley floor is already well below sea level. And those plates are still pulling away from each other at a rate of up to 1.5 centimeters a year. Which begs the question, what is the future of the rift? Along with other researchers, Nigerian-American geologist Dr. Folarin Kolawole has discovered fault systems that could potentially extend into South Africa and all the way to the Atlantic Ocean. Meaning that, far in the future, the African continent could break apart into islands, its fractures filling up with a new ocean. In the meantime, large earthquakes could become more common in the area. Kolawole is just one geologist tackling some of our biggest questions about the future of Earth's surface. Will there one day be a new African ocean? How tall will Mount Everest get? What will our planet look like as its plates keep pulling apart and crashing into each other? Only time and rocks will tell. Tell me your secrets, Dwayne! Our planet is full of wild, weird, and wonderful features, thanks to the forces of plate tectonics, from towering mountain peaks to vast valleys. Earth's land forms and deforms in countless ways that make us go, whoa. And while we do know how ancient marine fossils ended up on top of the world's tallest mountain, there are still many geological mysteries left to solve. Next time, we're diving into marine geology. See you then. Thanks for watching this episode of Crash Course Geology, which was filmed in our studio in Indianapolis, Indiana, and was made with the help of all these nice people. If you want to help keep Crash Course free, for everyone, forever, you can join our community on Patreon.